Okay, the record is on. Folks here back, and some of them are missing. But that anyway. Okay. Um, you can see if you look at the joint C now. I'm going to draw the free body diagram of joint C somewhere here because you can see member CD. You will not have shear force diagram or bending moment diagram because you don't have the force perpendicular to them. Okay. So now you can look at joint up. Yeah. You can look at the free body diagram of joint C. So what do you have? One of your friends is nice enough to adjust the size of the pen for me so that straight. Anyway, here you have 800. Let me try to find it. Okay. So I'm not going to change the color anymore. It's kind of painful. So that is also 800, correct? From the end of member BC. And then we have this upward. 3200 over 6. And remember that we have proved that moment at C is 0. Now, if you can recall, we have this external force 800 at joint C, which gives you the perfect equilibrium of sigma fx over there. That's why when you look at the other side of the joint, there's no more of 800. We already balance it by the internal force coming in from member BC and the external force at that particular joint. So it's gone. And all you have left is just force, the vertical force. So that explains why going from the free body diagram of member CD. So I might as well write somewhere that this is your joint C. Thank you for adjusting the different thickness because now my handwriting looks more humane. Yeah, okay. See, it does help this case. And of course, if you think you put free body diagram, equilibrium such, this should not stop you. You should be able to write the free body diagram of anything in the world. The one thing, I share you this before we go on. See, we all have the L-shaped sofa at home, right? Very fashionable thing right now. So when I ask my kids to help move the sofa, then I'll yell at them, hey, apply the force at the centroid. Because if you believe in equilibrium, every section has a centroid as you've learned, right? If you have a sofa like this, the centroid of the sofa is probably there. When you push the sofa here, at the end, what happens? It's going to happen. It's going to rotate. No, it doesn't move like that. It's just going to, it's perhaps going to go like that. And it moves like that. Right? That's simple knowledge that you use every day. But you don't have to move so far every day. So you don't just for curiosity, I'm just gonna go back and move so far every day. Prove my point about equilibrium. But you can tell your parents, be proud of me. I know how to move the sofa efficiently now. Right? But yeah. Okay, step. In the medical world as well, when you go when you get it over, you have a back pain and something like that. It's because you don't use equilibrium in your body posture. A bad posture will create extra bending moment somewhere. It's going to cause you back pain, the neck pain, the whatever pain. If you know how to adjust your body weight when you lift something heavy. Apply equilibrium. Right? And when you use the dumbbell like that, you know, this upper part of your arm becomes like a cantilever beam, and your lower arm, and then your upper arm becomes your fixed point. That's why you have the muscle over there by lifting up the dumbbell. Equilibrium. And you know, when people try to lift heavy stuff from the floor, if you use your back, it means you bend down, try to lift the stuff. You create bending moment at your back. And your back is not a structure that is created to withstand bending moment. So do you have back pain? That's why you need to just crouch down and lift up by using your legs. Okay, here we go. Right. Now we go back here and try to finish our shear force and bending moment diagram. Okay. Now we're gonna have the universal question that I get every. Look at the shear force diagram. Now it's a question of whether you are standing on the left or on the right of this member. Okay. If I stand on the right, this is my eye. I look that way. I'm going to see something like this. 800, 800, and 3200. Right? If I stand here and look, I will see 800, 3200. But wherever you look from, one thing never changed. That is this. Let's look at this first. This is the direction of the moment. All right. So when you look at the direction of the moment, where would the tension and compression of this member be? This member will have tension on top and compression at the bottom. While this will have compression and tension. Again, don't just take your time. We are talking about the same member, but we look at it from the opposite side. No matter what you do, this side is always under compression. See? Right? That is under tension. Now it comes the tradition. Have you ever noticed that all the classes that you have had until now, you always draw your bending moment diagram on the compression side of your beam? See, guys. We always draw bending moment diagram on the compression side of your member or your beam. Always. So that if I go, where's my simple beam? It's gone. When I try to demonstrate the curve, oh, it's not here. Damn it. Anyway, let's use this space. When you have when you have a beam with a simple vertical load, whatever that is, your bending moment diagram is always something like that. And you know your deflected shape is like that. So it's compression up top, tension at the bottom. You have bending moment diagram on the compression side. But if you have a cantilever beam, whatever that is, your deflected shape is always like that. And your bending moment diagram is always like that. It's on compression side because this is where the compression is, and that's where the tension is. Okay? Now, ladies and gentlemen, because we are in the international program, let it be known that some countries in the world draw bending moment diagrams on the tension side of your beam. So I was mocked when I went to, oh, you draw on the compression side. Yeah, we do. What's wrong with it? Like that. So if you go to the US of A, for example, they do that. Like that's bending moment diagram of that beam in the US. I'm not sure about England. Now, they draw it like that. They draw it on the tension side. We generally draw it on compression side. So I will assume that everybody will draw it on the compression side. Okay? So that means you may are you working on this? Okay. Okay. Oh. So when we are working on this, the direction of the shear can change, because it depends on where you look. But your moment diagram is always on the same side, because if we say we draw it on the compression side, there is no way you can swap the side. Because we have only one equilibrium here, right? Under one structure, under one loading condition, can only have one equilibrium. Can't argue with that. So that means when you complete your free body diagram here, you will know where compression is. And regardless of where you're standing and looking at the member, compression side will remain where it is. It doesn't change. So when I don't have to spend a lot of time with this, right? This is simple enough, but anyway. Right? Shear force diagram. Shear force diagram, that's minus, right? 800. And bending moment diagram, force, if you have the negative area, in the end, it should be the negative area. That's minus 3200. It's equals that, right? For this pink one, you begin with the negative shear as well. Downward. But your bending moment diagram is now like, you begin with a positive value and then the shear force diagram bring it down to 0. It's a shear force diagram. Wow. That's bending moment diagram. No, so direction becomes a little bit more important. And both of them are correct, depending on where you stand. Right? So let me tell you right now, this is not difficult, but it may confuse you a little bit. When you are confused, you're not sure about the direction. That means one thing: you lack practice. Because after all, up to this point, we haven't done anything differently from what you've done before in static or mechanics and materials at all. We just have one free-body diagram. And if you forget that this is part of the frame, it's just one free-body diagram, and you try to draw shear force diagram and bending moment diagram corresponding to this free-body diagram. Right? We haven't done anything more or less than what you've learned before. But now we just have the system that has more than one member. That's all. Okay, are you working on this? Can I go forward? All right. So now we can look at this BC. Nobody would want to just try to look at BC upside down, right? So I just going to proceed to the right. Okay. So for this BC, it's pretty obvious that we now have the shear. It's up on the left, down on the right, so it's positive shear. More diagram. That's pretty quickly. The 3 is kind of difficult because you have to change direction very quickly, right? All right. That's your shear force diagram. And look at the bending on the left. That's the negative moment, right? So we begin with the negative value here, and the positive shear area will bring everything back to you. Oops. You know, it would be nice if you could always write the unit. Yeah? So from meter, so from force, every time. But just I don't have a lot of areas, so sometimes I'm kind of carefree. It's not a good idea. Always try to have the unit with you always. Question? And then we're done. Because remember, CD doesn't have neither the force diagram nor bending moment diagram. But just to be sure that you believe, you're sure that I know what you know, maybe you would do well to conclude here as well that there's no shear force diagram or bending moment diagram for member. Okay. Question? Now, again, I should try to impose this OBE description on the problem. We have talked about this. Can calculate reactions 20%. So that means when you go back here, if you are here, all the stuff you obtain here, that's 20%. Okay. So let me write down somewhere. Here is level 1, 20%. Remember, you have to complete every free body diagram first. If you get this free body diagram of member AB correctly, and you proceed to draw shear force bending moment diagram, and then you cannot finish free body diagram of member BC and member CD, that means you're stuck at level 2. The complete free body diagram of member AB, here BC and CD will give you 24%. Because it demonstrates that you know the equilibrium. The fact that you try to do extra work by going on to obtain shear force and bending moment diagram of one member without completing the free body diagram of every member in the system will not give you extra credit. Complete free body diagram. So the free body diagram of AB, BC, and CD. Complete free body diagram to give extra 20%. So, because I think this is basic, and this is our requirement. So if you can come this far, just the free body diagram of everything, you will be right at the threshold of F, 40%. You need to be able to complete all the free body diagrams of every member and move on to the shear force and bending moment diagram to go over 40% threshold, just like statement. And you see, I have the prerequisition. In order to go to level 2 here, you need to get the correct reaction. If your reactions are wrong, you're stuck at level 1, no more than 20%. Okay? So let us come back here. We have 20 minutes. So that means we have more than enough time to finish our second condition. And then that's done. Okay. Now I change the support condition into a typical 1 fixed support. It is stable? Of course it is. Yes, it is stable. So let's work on that. Okay. Now, again, without further ado, this you should know right away that it is 800, right? And of course, there is only one support. So now you should know that there cannot be a vertical reaction. So this system gives you the couple of again 3,200 kilogram meter as a moment counterclockwise. So in order to balance that, the only way is to have the clockwise moment of 3,200 kilogram meter here. That's it. We're done with the reaction. Okay, so what you should be able to see immediately as well is that just going back to try to if I could use the same color, or I already did. Yes, fine. You can see right away that, you know, we have the external force applied here. So this member is nothing, right? Just there hanging around loosely like that without doing anything. So no force, right? No internal force. Why is it there? I don't know. We don't have it. We don't need to have it, right? Might as well just go do it. Okay? And I think it's pretty straightforward because let's call it the name. I don't even have to name that part, right? So it's just A, B, and C. So when you look at number B, C, and we work on B, C, or you want me to work on A, B, learn to be more flexible and start your work anywhere you can. Because apparently here, if you start from BC, it's much more convenient, right? Yeah. So BC. Now you have external force 800. What else? You use different colors so that you know this is the force that balances. So again, that's it. Can't have any more, right? Yeah. So that means BC becomes just something that you can call column, because they just axial force. So you can summarize here right away that on a very cool word that they like to use, by inspection. Member BC has, let's use cool English, right? Has neither SFD nor VMD. How do you like that? When you compose a sentence like that in IELTS, you're gonna get a good score, right? Woohoo! Can you come up with a new sentence without using mine? You can be more elaborate. So instead of saying it, you can try something like, from by the look of things, it can be clearly seen that member BC can not have internal shear or both. It's essentially the same sentence, right? And therefore, shear force diagram and bending moment diagram of this member will contain zero value. Make it very, very long. In fact, it's just the same meaning. You can elaborate it if you want, just for fun. Okay, done. So if you can see that, it means that the analysis of this frame comes down to just member AB, right? It's just the only thing that we have something going on. Right. Have reactions. And we have the force 800 from this member BC. So it comes in the direction opposite to that. Would you look at that? Wow, our sigma effects balance itself out beautifully. right? Don't have to do anything. And now you see that the two forces again do not coincide. So it means we need to have moment. And in this case, the moment better be equal to that. Because from member BC at joint B, you don't have moment. So that means when you move to member AB, joint B better have no moment as well. And basically, of course, you may want to prove it. So sigma MA equal to 0. So MA is equal to 800 multiplied by 4, right? Because the member is 4 meters long. So that's 3,200 kilogram. What do you think this is? This is essentially a cantilever beam, right? When you turn this 90 degree, right, you see it's just cantilever beam, or to the left. Okay. So again, when I put this way, my G1 diagram is negative 800. And my bending moment diagram would be linked from the positive value for 3,200 and brought down to 0 by the negative G1 diagram. Okay. You can practice by writing the bending moment diagram from another side, but you don't need to. Okay. Any question? Folks at home, you don't have any question today at all? Let's try. I'm not going to begin the new problem because we only have 2 minutes. And let's try doing something more fun. Okay. Okay. Guys, ready? Painting something? Painting it over. Now, we know that the compression is oh, no, not. That's where the compression is. So, can you see how the beam is going before for your member? You have 800 here, pushing it to the left. So without any analysis, you would feel that, okay, your structure should go like this. And because this is cantilever, so your 0 rotation is there. Can we do that? If I look at the same beam, but then I switch everything and I redraw my free body diagram. That's exactly what it is, right? That means you can clearly see that this is going like that, right? So we superimpose there here. That's what you get, right? And what else would happen? Member BC and CD both have no moment. What do what it means? Does it mean they remain straight, right? Because there's no moment. And look at joint B. This is the rigid joint. So it better maintain the angle. So that means BC go up. Right? Straight line. And if we move to the left for say 30 centimeters, C better move left 30 centimeters as well. They gotta go together. And what is that? Another rigid joint, right? CD has no moment. So yeah, there you go. It's gonna go like sense, right? Oh, not done yet. We have another coding condition, right? Are you done with this? Let's go back and finish this one. How do you think it would go? This guy, AB, look at this. That's a hinge, right? So it better go like that. Do you think so? It is. Try looking at this. Or this. But then again, you need to draw the support to see the picture better. So I think the pink one would be better. Well, support it, right? Okay, it moves like that. And now, when we move, C must move as well. So it's pretty much the same. Okay. And because this is a rigid joint B, when this rotate a little, it has to maintain the angle. So we will have a rotation like that. Right? And look at BC. Oh, you have the negative moment. Right? We look at bending moment diagram, remember BC is negative moment throughout. So it's a negative curvature. Correct? Now we must be true to what we have here. Right? A lot of students will go wild, you know, try to sketch different shape. Now we have a negative moment here, so you must be true to what we have. So that means your curvature for member BC must remain negative, and that's negative curvature, right? The frowning face. And again, because joint C is rigid, if this had the angle, you know, rotates like that, this must maintain the rigidity. Therefore, since member C doesn't have any moment, it must remain straight. what you have. See, no calculation required. Just understanding that you have from your mechanics of materials, and that we haven't done anything new with it. We still have a few minutes left, and I think the most important thing is just not to draw the picture that I following my drawing, just to try to make notes of what I just said. Okay, so if you forget any part that I just said, please ask me now. I'll try to make notes now. Okay? My structure analysis is a piece of cake. Straightforward and easy in terms of mathematics as well. And it all seems reasonable until it becomes unreasonable. Right? So now it is reasonable. But I think, say structural analysis is has a direct relationship with mathematics calculation. So it looks pretty straightforward until now, simply because we have made necessary assumptions to make it straightforward. So as long as you are in the elastic world, it's still straightforward. But the world is not so elastic, is it? Nothing is elastic. Yes, something is elastic. Yeah. It's hard to find a perfectly elastic all the time. So I think that's it for us today. Again, don't forget that the homework should be turned in on time. Okay. I think we've gone back to the same world where I graded and I'll upload it by using the Google, whatever they call it, Google something like a Dropbox. Huh? No, not Google Classroom, just Google Drive. Yes, that's what's slipping my mind. And I'll give you guys a link. Okay. We are going to have the active session again tomorrow, but I think it would be better to have just online only for another week. Okay. Okay. You guys can continue to work on the floor plan, or you can start working on your frame. Keep in mind that what we have today will not be in your midterm one. Okay, so I may not have a lot of customers tomorrow because you don't want to do it now. But again, yeah, it's better than to hit the iron when it's hot, right? Second, next week will turn into your reading week, but I am always available. You have to let me know. Otherwise, I will not show up just to wait for somebody to show up. Active sessions are also available if you want it. Just let me know. Okay, that's it for today. Thank you, everyone. Thank you.